Yes, the title is the implementing monad in Python, and the main part is to understand what is the monad. So in this presentation, we will regard monads as a design pattern, something that is very computer science, even though the origin comes from category theory. So this is in the intersection of two areas, mathematics and software engineering. And it is used in lots of functional programming languages, such as Haskell, Scala, and F Shum. And today we will see two examples of monad implemented in Python. So Python, I suppose, is much more popular than these three functional programming. Generally, the picture is something like this. We have some value, and we want to put this under some context. And sometimes people use the word wrap some value around by some box, and this box will provide some additional information about the value. And the problem is to handle some function composition problem, because the type is different now. You can regard this as this one as some data structure, a new data structure that contains the value plus some additional feature. And what do I mean by that? You see some example. And first, let's start from the beginning. Function composition, as in mathematics, is like this: A, B, and C are some set. F is a function, G is a function. We can compose F and G and call that H. So that is very basic. H can be written as G after F. So in mathematics, we usually say G compose F. We apply F first and then apply G. We may also say G after F. So F go first. This apply F first and then apply G. So that is function composition. This is mathematics, but in today we will apply that to computer program. This set here is replaced by type. So string is a type, string type, and the green area is the floating type, floating point number. And we will look at two functions from conversion from string to float, and then take the inverse. So this is a function composition. Apply a transformation from string to float in the first step, then take the multiplicative inverse. And of course, there are some problems. We call this the partial function, because not all string correspond to some floating point number. So the successful case is like this. Oops. Something like 102. This is a string. So that will map to, of course, 102.0. That is a floating point number. That is the normal case. But string could be 1A3, 1A23. So what is the value of 1A23? Of course, there is no such value. Then we will have an error. That should map to something else, maybe exception or error. So that is the meaning of partial function. Not all elements, not all string can be converted to float. That is something very, very easy to see. Float. Now let's look at the second part, second function, inverse. We have a famous exception, because 0 cannot map to any, cannot be mapped to any floating point number. So that is also an error. But any other float has no such problem. For example, 102.0 will map to 1 over 102.0, whatever that is. So this is the problem. Sometimes you have error or exception, and the monad is created to handle this kind of problem. Function composition of compositionality is the keyword for today. We will see some example in Python, but first I would like to show you some high-level picture first. So that is called exception. So this is precisely what I drew in the previous page. Some string has no output, and in Python let's use the keyword none. None does mean error or no output or exception. So it has to be treated as an exception. So now this will pose some problem in function composition, because if the element is none and we apply none to inverse, then what should we get? We should also get none. Okay, so this is some kind of programming problem or programming technique. So that's why monad in today's presentation is regarded just as a design pattern. Some design pattern that occur quite frequently in programming, and we abstract the essence of this kind of programming design or software design pattern. So that is another viewpoint. So let's handle the exception by creating a new class. And this new class is regarded as a data structure. The new thing we add is the none value. If we start with anything with none, then we have to map to none. That means no value. That will always follow this path below. If once we have any error, then we will always stay in the path in that follows the none pattern. If there's no error from the beginning to the end, then we will follow the upper path. So this looks like a railroad. And let's see how to implement that in Python. And to do that, the monad is like a lifting or elevating from the normal world. Normal world is in the ground floor. From string to float. And we try to handle the exception by some elevated type or embellished type or some extended type. So E here stands for extended or elevated. We will include one more feature. We may have no value denoted by none. And a function f must be elevated to a more complicated, slightly complicated function. We call this elevated f or extended f that map from a new type extended A to extended B. We also need to write another function denoted by EG that map from extended B to extended C. So that is something we need to do as a programmer. And here we call this monadic. Well, we will not define formally what the monad is, so you have to guess what that is from the example. Okay, so the first thing that I would like to introduce is called lifting or fmap. In functional programming, it's also usually called fmap. And this is the process that elevates or lift from a normal function. So this is the normal, let's say, string to float function. Elevate that to an extended function with new input type and new output type. And the signature is that given any normal function from type A to type B, we will create a new function from the extended type A to the extended type B. That is called a lifting. So this is one way to solve the problem that I just mentioned. Okay, so let's now consider an example. Okay, so today is just playing around with Python. And let's look at the upper part. I define a function inverse. So that is just take x and return 1 over x. And of course, x cannot be 0. If x is 0, there is a runtime error. And input is some string. A is the input, some string 2, 3, 4, 5. it convert that to a floating point number by this float, and then take inverse. The output is C. Okay, that is the usual case with no error. That is the output. 2, 3, 4, 5 inverse is this number. The value is not very, has no meaning. I just randomly pick some number. Let's see some error type. Suppose we have some English letter alphabet then this is not a float. If we run this, we get value error, cannot convert to a string. Okay, so that is the error that we want to handle. But if we have E, so 2, 3, 4, E5, what is the output? That is okay because it is a scientific notation, 2, 3, 4 times 10 to the power 5. So this one is no error. But if we input 0, then it can be converted to float successfully, but it failed the second step. The inverse has error, float division by 0. So we have two types of exception or two types of error, two types of failures. And let's try to solve this using a data structure. So that is called extended value. 10 has no problem. Okay, 10 has inverse 0.1. Okay, to solve this problem, let's try to use extended value. This is a class containing two values. The first value is just the ordinary value. And the type is dynamic. So Python is dynamically typed language. It could be string and could be float, depend on the input. And we have one more error flag in the data structure. Error flag is a Boolean. By default, it is false. False means there is no error. Error flag is true, means there is some error. So we do not want this to be true. We want this to be false all the time. That will be the successful case. Okay, so that's called error flag. We add this new Boolean variable, and to print out, I use this string method. Just print out the value and flag in the string in the same line. So let's try to play with this first. So extended value. If we input 10, so let's call this A. A is the extended value. Then what is A? Let's print A. So the value is 10, and the error flag is false. So false means no error. It is okay. So the default value is false. So that is a good thing. We do not want true. True means some error has occurred. Okay, so that is the data structure called extended value. And suppose we want to convert 10, this string 10, to a floating point number 10. And let's directly repeat this. B is float of A, and what is B? So can we directly apply float to 8? And of course, there is some problem. If you run this type problem, float has input type string or some other or integer. So we have not defined the conversion from a string from this data structure extended value to a float yet. So this is something that has not been implemented yet. So you can see the type error. Float argument must be a string or a number, not extended value. Okay, so something has to be done. So the naive way is to rewrite the string to float function that takes an extended value as input and produce another extended value, and also rewrite the inverse function that takes the extended value as input and produce another extended value. And if our process has lots of such steps, then we have to do this writing revision for each of the function. So there is one way to do all of them in one step. And this is the lifting that I'm going to type. Okay, so let me introduce this new function. Lift is a function that takes an ordinary function f as an input. So the f here is an ordinary function such as float and inverse. And the purpose of lift is to elevate it or lift this to the second level that takes the correct type as input and produce the correct output with the correct type. Okay, so what we need to do is also very straightforward. There's only one way to proceed. So first check whether this is true or false. If this is true, that means something wrong has happened. Then we just return the same thing. No calculation is required because the input is nothing. Return the same thing. So if this is false, then we can try to do some calculation. Let's evaluate the function f. So this f is the input. Compute a value v as f of self.value. Apply the function f, which is in the input, to the value in the data structure. The new value v is something that we need to return. Return not just v, return the extended value of v. And by default, the error flag is set to false. So that is the case with no error, but there could be some error. So the exception, except if any error occur, then we return another extended value, but now the value is no value, and we set the error flag to true. So that's all. That's the lifting function. Okay, so now let's try this. A is equal to extended value of 10. Now let's take a dot lift float. So this will lift the ordinary function float to the monadic well that takes an extended type and output an extended type, and then we print B. Okay, so this is now, there's no type error. It will accept the correct variable with type extended value. So the output now is 10, but 10.0. This is a floating point number. Error flag is false. And next step, we can do the inverse. B and have to lift the inverse function. So in Python, function is a first-class citizen. So we can treat this as input or output or just some object. And print C. So see what happened. The answer is 0.1 as expected, and there's no error. Error flag is false. If there is anything wrong, suppose we change that to 10 ABC. So it will fail in the first step. B is already none. And if we run this, the output is none and true. So as we correctly handle the exception. And let's see also the 0. If this is 0, then it passed the first step, but it failed the inverse. It's also none true. So no error, and the error flag is set to true. Okay, so this is the lifting, the concept of lifting a function from one world to the other world. In category 3, we say it's a functor from one category to other category. And let me show you something that is very cool. And override this OR function, double underscore. So we define the OR operator to be the lift just return self.lif f. Okay, so with this new notation, then we can do something that is very compact. Extended value, let's say we input 10. If you know Unix, then this is very close to Unix pipeline. Pass that to float and then pass that to inverse. And see what happens. Let's call this A. This is an extended value, and then we print A. Okay, so one line, we can compress the previous 3 lines into just one single line. That is very, very nice or elegant. And if there's any error, suppose there is a string HJKL that has no meaning, so should be some error. If we run this, the error flag is set to true, and the value is none. So everything is behaving as expected. Okay, so that is the first example. This is called the maybe monad. Maybe monad means we introduce a Boolean variable. So the value may be none, maybe nothing. And in that case, if we have a nothing in any intermediate step, then it will stay to be nothing throughout the whole process until the end. So this is one way we can implement this type of error handling or exception handling. All right, so that is our first example. This is called maybe monad. Now let's do the second example. Second example is this type of cross-row function from the ordinary row to monadic row, from type A to an extended type A. G is from type B to an extended type C. Okay, so F and G are functions, but the problem is they do not compose. We cannot apply G after F because the type does not match. G is supposed to get a type B variable as input, but the output of F is an extended type B. So the type mismatch is the problem that we want to solve. Okay, so let's see the Python example first. So we'll illustrate this using a second example. So this is our second monad. Second example. Yes, right here. So this is called a locking, software lock problem, but not the problem, it's software locking process. Instead of just running the program, we also want to record the event that has occurred during the program or during the process. So here I'm simulating two process or two functions by add 1 and multiply by 2. And I introduced an arbitrary delay. We sleep for 0.1 second in the process. So it's supposed to be a very slow process. And this is add 1 and multiply by 2. And so I use the sleep function from the time library. So let's first see what is the behavior. And let's start with A is equal to, let's say 10, and we add 1 to 10. So add 1 is a function or a process. Then the output is 11. Okay, so very simple. This is just some simple function. And the thing that we want to add is some login information, some message. We call it time information. So instead of just returning 1 plus x, we also so interested to see at what time this is computed. So let's input another function, skey time. ASCII time, we print out the current time. 1 plus x, we also add return the function. Let's type this is a f and f string. We run the function add 1. And also we call the time by concatenating ASCII time. This one is multiplied by 2. We multiply by, we don't need f here. Multiply by 2, and also record the time. Okay, so we want to add this information, and this is what the picture at the beginning. We want to provide some context. We extend this or embellish, add some feature to the original value, and that will cause some problem in function composition. But let's just print out add 1 to 10. And what should be the output? If we add 1 to 10, the output is 11 plus some additional information. That is, we up the function name, we add 1, and the time is Saturday, July 18, 11 o'clock. So, and we want to record this for the two for any function application. And suppose we multiply by 2. Then what is the output? We will get 20 plus the time information. We apply the multiply by 2 function at this time. How do we put them together? We want to add 1 and then multiply by 2 and save all the log function, the message, together in one single string. In general, we may add 1 multiple times and also record all the time information. And suppose we do concatenation, multiply by 2 and then add 1. There should be some problem because the type doesn't match. So let's see what happened when we run this program. So when I type 1, then error, unsupported types, because this is not implemented. We don't know how to add 1 to a tuple. So actually, we are returning a tuple. This is a tuple with the first component equal to some number. Second component is a string. So this is a new type. We cannot compose the 2 functions directly. Something else must be done. And this something else is the monad. Okay, so now in our second example, we will use another method. There's no class. So let's try to implement the monad without any class. Okay, so that is the problem. So let's solve this problem using the terminology from the literature of a monad. Okay, so the cross-row function do not compose. So this is my running example. The value here, A, B, and C are just some number, integer or floating point number. And the extended row, monadic row, is the number plus the time information. So that's why I put a box or a square around this type. Some more context is provided. And F is the function that I just typed. Take a number as input, add 1, and append the time to the end. Okay, so but the problem is that F and G does not compose because of type error. Type does not match. So that is the program log example. We record all the events that happens when we run a program. And let's solve this by this concept called bind, also called flatmap. If you know Python, then flatmap is something that occurs quite often. And in Haskell, this is the notation, this is also often called a fish operator because it looks like a fish. And the transformation is take this function f as an input, take this as an input, and extend that to this function from extended A to extended B. Then we can do the composition more easily. Okay, the signature for this bind operation is we take a type of extended type A, take something like this, and also take a function f with signature from A to extended B. So that one is this f. Take these two inputs and produce a new function. This function has type extended A to extended B. So that is what a bind operation is. Okay, we will see the, if you think it's abstract, then we will see a concrete example very soon. And another one that we need is called unit, also called return or pure. And because this type of concept arise so naturally, different area discover the same concept independently, they give different name to the same concept. So therefore, there are lots of different terminology. It's one reason why this area is difficult to understand, because there are too many different type of notation. Like unit is come from the mathematical side. Return and pure, so return obviously come from the computer science. So this is just taking an object of type A, take some A, and enclose it using the box, return an extended A, and that's it. So signature is take some number or some value with type A, and close this using the box, and return that box. So wrap this around and return an object in with type extended A. So just a transition from the normal world to the monadic world. So that is called a unit. Okay, so that let's see how this works. Okay, that is our Python notebook, and now we'll implement bind and unit. Let's type unit first. Unit is easier. Unit is another function. Take some value as input and return an extended value. And here, in this example, extended means we append some time information. So this one is initialized, init the value to the value. And then at some time plus the current time. Also, let's return. Let's look at this first. And instead of 10, unit 10. A is now an extended value. And let's see what happened. No output. Let's print A. Okay, A is a tuple, or it's a pair. The first one, the first component is a number 10. We initialize to 10, and the message is init to 10 at the current time. Okay, so that is just a unit. Unit is just a conversion from a normal number to an extended type, a number plus some time information. So that is unit. And second concept is called bind. Bind will take a function f as an input. Okay, f is going to be add 1 and multiplied by 2. So here f is a function. bind will modify the behavior of the function f. And now we will use another trick from Python. This is a nested function. Inside this function, we define an inner function. Inner function, let's call this inner t. T stands for tuple. T is a pair. Take a pair of object and apply the function f to the first component. Okay, so T is a tuple with index 0 and 1. So T0 is the number. Apply the function f. F is this value, input value. The input value is a function for bind, and return a tuple. So this one is the tuple y and m, as expected, because now add 1 is returning a tuple. Multiply by 2 is also returning 2 things. Okay, so y is the value. This is the y, and m is the message. M is the time message. After this, we have to return a tuple. So here, usually a tuple here is enclosed by parentheses, but you know that it is optional. Return the value y and t1, the original message from previous steps, plus the current time message m. And let's also please put a new line character at the end. This is inner and return inner. So bind function will return another function. This function inner will add some additional feature to the original function f. The additional feature is precisely described in these 2 lines. Okay, this is bind, and let's apply bind. Add 1 become bind of add 1. So we define add 1 by binding this to the new data structure or the new extended type. And multiply by 2, we also change this. Multiply by 2 is now bind of multiply by 2. So first check that there is no this. So multiply by 2. Then no typing error. And now let's see what is the behavior. Instead of add 1, we have a new add 1 and new multiply by 2. So that's type B is add 1 to A. So we call that A is a tuple containing two pieces of information. And now we print B. And let's separate that B of 0 and print B of 1. Okay, B of 0 is the number 11, add 1 to 10. And the time information is now a string initialized to 10 at some time, and then we add 1 at some other time. And we cannot see the difference in time because the time is too short. Let's increase that to 1 second. Multiply by 2, we wait for 2 seconds. Okay, so now we wait for some more time. If we change that, let's see the difference in time. So initialize as 11, 12, second is 52. Second is 52, and then second becomes 53 because we wait for 1 second. And also let's complete this example by multiply by 2. And let's call the output C. And what is the output? Have to wait for more time. Multiply by 2. Wrong typing. No I. Now the answer is 22. 11 times 2 is 22. And we have 3 steps. Initialize to 10, add 1, and multiply by 2 at these 3 different times, and all the time are different because the time are deliberately made to be very long. Okay, so this is one way to solve the composition problem. Now there's no such problem. We can now compose add 1 and multiply by 2, even though add 1 is a cross-rel function. So notice that we modify the behavior of add 1 by this binding operation. Okay, and if you know Python, then you know that there is a even better way to do this binding operation using decorator. So instead of add 1 equal to bind add 1, we just comment out. So just bind. This is a decorator. The effect is the same. This is equivalent. So this bind, this decorator is equivalent to modifying add 1 at the end by binding add 1. So these are exactly the same, but of course the notation is much cleaner and more compact. And let's try this. No error, and also print out the correct expected number, expected input, or expected output. So 22 is the final answer, and these are the step and the time. The use of, there is a question from the chat. The use of sleep is to wait. So because we want to wait for 1 second and wait for 2 seconds, sleep just tell the function, tell the program, just delay or just wait for 1 second and 2 seconds. Okay, so this is sleep. This is a function from the time library. Sleep does not show the time difference, just a time. It's just a time delay. It's like telling the program to go to sleep for 1 second. We can change that. Suppose I change that to 5 seconds. Then that we have to wait for a much longer time. So suppose this is sleep 5. That means in this function, it will take 5 seconds. Let's run this. Okay, so I have to wait for 5 plus 2 seconds. Wait for 7 seconds, then we get an output. Okay, so notice the difference between time. Init is at time 16. 16 plus 5 is 21. Okay, add 1 is done at 21 seconds. 21 minus 16 is 5. So that is the purpose for sleep. So why do we call sleep here? If no, then I cannot demonstrate the time information. Suppose I comment out. Yeah, so you ask a very nice question. Suppose I just remove this, then all the time are the same. Then I cannot demonstrate the functionality. What is the difference? They are all done at 11, 16, 57. So they are all the same, which is true, but does not demonstrate my purpose. So I deliberately, artificially introduce some delay so that the time information are different. So this is a simulation of some process that takes some time. I don't want to write a very long code that takes a lot of time. So just type sleep to artificially introduce some delay. Okay, so let's do one last example. And suppose I sleep for 1 second for add 1 to demonstrate the composition. So instead of multiply by 2, I add 1 3 times, add 1. So I add 1 3 times. The answer should be 13. So what is the output? So this demonstrated composition is now no problem. It's very easily done. So we apply the function add 1 3 times. So we notice the time difference. The first add 1 is executed at 25 seconds. Second add 1 is done on 26 seconds. The last one is 27 because I introduce a 1 second delay in each function, and the answer is 13. Okay, so this solves the composition problem using this bind operation. And this is monad. So if you ask what is monad, then what you are looking at the screen is a monad. For a computer scientist or software engineering, monad is some design pattern that occur quite naturally or quite often in their daily life because of this type difference. Very good. Then this is what I want to demonstrate today. And summary, we have seen 2 different monads. The first one is called maybe monad. We add 1 Boolean value, and we implement this using a class. And second monad is called a writer monad. We write some more information to describe the function or describe the process. For example, this is a log problem, the software log file. We want to record all the events, what happened, and at what time that function is executed. And we see that this can be quite easily done using the bind operator. That is called a writer monad. And by this, I hope that this is some motivation to study category theory, because lots of monad is quite abstract, and this example show that it is not that bad. This can be implemented fairly easily in Python. Let's another question from the chat. Print B directly. Yes, so let's print B directly. B is a tuple, so if we type just print B in 1 line, what is the output? If we run this, then we wait for 3 seconds, and then we get a tuple, a pair. The first component is the value. Second one is a string, but this is does not look very nice because the new line characters are displayed as \n. But it contains all the information, just does not look nice in this format. Printing B directly is this. Nothing changed, just different presentation. Okay, any other thing that you want to ask? That's all I want to demonstrate today. Maybe one last demonstration. Suppose I change the middle at 1 to multiply by 2. Then what is the output? So here the purpose is to demonstrate the flexibility in composing the function. You can compose in any manner, so no type error. Output is 23, and because this is not very nice to read, I separate this in 2 parts. Then the string will be displayed in 4 lines. In each add 1, multiply by 2, and then add 1. The answer is 23, and all the time information is recorded. This is the question is this functional programming? So this is using the idea of functional programming. So my answer is yes. For example, we are using this bind. Bind takes a function as an input right here. So this is some feature of functional programming, but you are correct that Python is not a functional programming language, but it contains some feature. For example, here I'm using the feature that a function is an object in Python. A function is a first class object in Python. We can pass it to a function. A function can return another function. So we are using this feature to implement the monad or functional programming feature. But strictly speaking, Python is not functional programming. There are other component of functional programming that is not available in Python. Okay, so okay, if there's no other question, then we will stop the recording. Thank you very much for coming this morning.